We will talk about Python and MapReduce programming with Pydoop. Python and programming you already know all about, so we will try to say something about MapReduce and Python. Okay, this is, first of all, start with some acknowledgements. This is something, it's a famous article you might have seen on the web. The Dr. Journal is a famous, well-known article by Dr. Sutter, and it's called "The Free Lunch is Over." What does that mean? Can you see the dark blue curve there? It's the increase in CPU clock speed. Around the year 2004, the clock speed kind of accelerated. It is not increasing anymore. This is due to difficulties in thermal dissipation. So the number of transistors is still increasing, but the CPU clock doesn't go up anymore. So what's the free lunch? The free lunch, the one you could have until 2004, consists of the fact that you run a software and then you can just sit back and wait for CPU clock to go up, and your software's performance automatically went up without the need to do anything, simply because of the fact that you had faster machines. But that's not true anymore. What you get now is that you get more cores on a CPU. So if you want your software to be faster, you have to master parallel programming techniques. What was once the domain of some experts now must become commonplace. But you might say, okay, what do I need? Why do I need my software to be faster? It's just fast enough as it is. Well, that might not be the case. In many fields of science and industry, there is a recent phenomenon which has been called the data deluge. There are many fields where the amount of data to process has increased tremendously. So these are called data-intensive applications. Sometimes, from an algorithmical point of view, sometimes the applications are not even that complicated, but the sheer fact that you have to process a huge amount of data means that you need a distributed programming framework. So we will talk about a specific programming framework, Google's MapReduce, and in particular the most important open source implementation, Apache Hadoop, and we will talk what are your options for writing programs in Python for this framework. And specifically, a package we wrote in CRS4 called Pydoop, which is a Python API for Hadoop. Okay, so here is the outline. So we will talk about MapReduce and Hadoop. Then there will be a brief course on how to install, configure, and run examples on Hadoop, and then we will talk about the Python package. Okay, so what is MapReduce? MapReduce is a programming model for large-scale distributed data processing. It is inspired by the MapReduce functional programming. The model assumes that data are organized according to a key-value pair flow. So the map function receives an input stream of key-value pairs and emits intermediate key-value pairs. Then the reduce function receives a key and all values corresponding to that key, and performs a reduce function on the set of values and emits the final output key value pair. But MapReduce is not only a programming model, but also an implementation of a system to execute such programs. And it's designed to be highly fault-tolerant, scalable, and relatively easy to use, because all internals related to low-level parallelization tasks like fault tolerance and necessary execution of failed tasks, and load distribution, load balancing. All these things are hidden from the user. You, as the programmer, only have to write your mapper and reducer components, and the distribution of computation and data is taken care of by the framework. So, in an age when everyone must go parallel, this is a nice thing to have, because you don't have to be an expert in the parallel programming domain to use MapReduce. You just have to master the programming model. So here is the MapReduce's Hello World, the mandatory work count example. It is a typical example of a data-driven application because it is actually a very simple task. If you have to do it on 1 megabyte of data, but it's not so simple if you have to run it on maybe 1 terabyte or 1 kilobyte. All you have to do is simply to count the occurrence of each word in a given amount of text. So here is how the model works. The text, the input data is split into subsets, and every subset is assigned to a mapper. Input data is a string containing the words you have to count. So all the map function does is splitting the string into words and immediately the word itself as the key and the number 1 as the value. Now the framework does automatically for you performs a shuffle and sort phase where key value pairs are sorted and grouped by key, so that each reducer receives a key and all the values corresponding to that key. At this point, it's very easy to implement the reduce function. You only have to sum together all values corresponding to that key, and you're done. So here is a pseudocode description of how you would implement this. The map function receives a key and a value. In this case, the key does not matter. The value is a string containing the words. For each word in the string, you emit the word itself as the key, and the number 1 is the value. The reduce function receives a key and the numerator over all values corresponding to that key. So you only have to sum together all values corresponding to that key, and that's all. Here is a mock implementation that I wrote with Python just to get the idea of what are the responsibilities of the framework and what are the responsibilities of the programmer. This is, of course, a mock implementation. It's not going to scale to a terabyte of data because it puts everything into memory. It's just to get the idea. This module, mock.mr.py, represents the framework, the MapReduce framework. So what does it do? It takes input data and a map function or a reduce function as arguments, and it instantiates a buffer, and then for every line of data in the input, it feeds sorry, the line itself to the map function, and then collects the output key value pairs, puts them into the buffer, sorts it. Then I'm using other tools to group the key value pairs by key, as the real thing does. And then I feed these to the reduce function, and I collect the final output key value pairs and bring them to output. This module represents a mock implementation of the word count application. So you import the MapReduce module, and this is just the same we have seen in pseudocode a few minutes ago. So you implement your MapReduce function, you give them as arguments to the MapReduce framework along with the input, and that's it. If you only have maybe 1 megabyte of data, this is going to work, but this is, of course, this is not the real thing. Let's see how the real thing works. instead. First of all, the MapReduce framework takes advantage of a distributed file system. Input data is stored into a distributed file system, and when the user wants to submit a job to MapReduce, the framework splits input data into subset called input splits, which are stored in a distributed file system. Then splits are given as input to mappers that perform what they need to do in the map function and write intermediate key value pairs to the local disks. Reducers remotely read the key value pairs from the disks where mappers store them and perform the reduce function and write the output back to the distributed file system. Okay, here is a comparison of MapReduce with similar alternatives from the 2 point of views of the programming model and the organization, the amount of structuring in the data. So MapReduce is somewhere in between in both dimensions. So it's not as structured as a DBMS, which is a with highly structured data. But there is some structure because from the computational point of view, we have a stream of key value pairs, even though data is read from flat files. And also it's somewhere in between the procedural and the programming model. This is a bit more detailed comparison between MPI, MapReduce, and DBMSs. The most important things are, first of all, the amount of data you have to process. MapReduce is especially good for very, very large data sets where data is written once and for all, and then you have to do a streaming batch processing of your input data. Do basically the same thing over and over again and write your output back to the file system. It's good when you have low communication between tasks. Basically, MapReduce is called a shared mapping architecture. There is no shared memory, no shared mapping. Every task is independent from the others, and this is different from one of the biggest differences with respect to DBMSs. And it's also relatively easier to learn with respect to the other models. But the most important thing to remember is that there is no one-size-fits-all solution. You have to decide according to your problem, to what the problem is. If you have huge data sets and you have to do a streaming batch analysis on them, probably MapReduce is a good thing for you. So let's talk about MapReduce implementations. First and foremost, there is the original Google implementation of MapReduce, which unfortunately has never been released to the public. But they did publish some papers around the year 2004, one on MapReduce and one on the distributed file system, which in Google's implementation is called the Google File System, GFS. And around the same period, there was Doug Cali, an engineer which was working on an open source search engine, and he found out that the search engine did not scale up to, it had scalability problems. So he read Google's papers and decided that that was the right thing to do to increase scalability in his project. So he started work on an open source implementation of the MapReduce framework, which is called Pydoop. And Pydoop is now a top-level Apache project with strong support by Yahoo, and it is also supported by other companies, but Yahoo is the most important, and it is also the biggest user and the biggest contributor to the code base. Yahoo now runs that there are separate clusters that run Pydoop, but overall there are about 35,000 machines running Pydoop at Yahoo. So it's the biggest user, but also other world-class companies are using Pydoop for real production work, like Facebook, eBay, Amazon, Twitter, and this kind of companies. So it's it's by far the biggest and most important implementation of MapReduce around. For completeness, we also have to mention DriveLink, which is a similar framework, although not exactly MapReduce. It has a slightly different model, but it's similar in spirit to the MapReduce framework. And there are also alternative implementation of MapReduce, but they are not as widespread and production ready as Pydoop. So we will concentrate on Pydoop in the following. So Pydoop is a distributed computing framework which has its key feature is high scalability. You can run it on thousands of nodes on very large files and a huge number of files which can be very large. It works on commercial off-the-shelf hardware, so you don't need to have a supercomputer with InfiniBand and fancy interconnection, etc. You just need a Beowulf kind of cluster with basically a bunch of computers interconnected by the local network, and you can run MapReduce. The thing you have to remember is that because it's organized in a master-slave fashion, and there is no backup for the masters, at least the masters must be more reliable than the other nodes. It's not a big deal if you lose a slave node, but losing a master node means that the whole thing goes down. Pydoop is especially well suited to backup tasks applications. So it's where basically these applications are applications where you have to, as I said before, you have to do the same thing over and over again on a huge amount of data, and they are independent of each other. It also has a huge aggregate bandwidth, thanks to its write once, read many storage model. This is a constraint that simplifies the handling of consistency between replicas, because files are stored in the file system with replication for fault tolerance. And since they're write once, read many, so once written they cannot be modified, this makes it easier to handle concurrency, to handle consistent with replicas, and so it allows to get a huge overall bandwidth. This, of course, makes it non-POSIX compliant, but so it's a specialized consistent for a specific domain. Okay, so here is a sketch of the architecture. Both MapReduce is composed of two main entities. The MapReduce Pydoop is composed of two main entities: the MapReduce framework and the distributed file system, which in the case of Pydoop is called HDFS, Pydoop Distributed File System. Both of them are organized in a master-slave fashion. The HDFS master is called main node, and the slaves are called data nodes. And the MapReduce master is called the job tracker, and the slaves are called task trackers. So what happens when a client wants to submit a job to the framework? It issues a job request to the job tracker, and the job tracker communicates with the main node, and to get the addresses of the hostnames of the data nodes where data blocks are actually stored. This is a key feature, the most important feature in MapReduce's architecture, because in this way you can move computation to data instead of the other way around. Moving data is very expensive. It's going to lead to an increase in traffic in your network. What MapReduce does is the opposite. Since it knows where data are stored, it schedules tasks closest to where data actually resides. So you don't have to move data around, and this is a key performance feature. Okay, here is how the file system works. So the data are stored with replication or fault tolerance. By default, the number of replicas is 3, one on the same rack and the other one on a different rack. This is in this way, if an entire rack goes down, maybe due to a power outage or something like that, you can still recover your data. So it's a fault tolerance thing. The data nodes are the components that actually store data blocks. Every data block is stored as an ordinary file in the local file system. The name node is the component that holds metadata and exposes a namespace to the outside world, which allows you to see sets of blocks as files. So from the outside, you see the whole thing as an ordinary file system. You see files and directories, and the low-level stuff is managed by the name. So let's say I want to read a file called A. I contact the name node, and the name node responds with a set of block IDs and their host names. At this point, the client can read data directly from the data nodes where those blocks are stored. This is also a key design feature, because in this way there is no data flow across the name node. Since the name node is a single machine, that would be a bottleneck for the entire system. So one of the key design features in HDFS is that there is no data flow across the name node, and all clients can read data, actual data, directly from the data nodes. Okay, here is an example of how you would write the word count example, the word count application in Java. This is taken from the official Pydoop examples, and this is not even the whole thing. I removed the leading imports and the training main program. So it's no wonder that many people don't want to write their applications in Java, but we will get back to that later. Just remember this program. It looks like a bit too much code for such a simple application, right? So, but we don't like Java, right? We like Python, so that we will talk about what you can do to program in Python. But first, we have to introduce some additional components. We've already seen the MapReduce. Those are the most important, the only required components. Every MapReduce application has these two, but you also can write additional components if you want to change the behavior if you have something more, if you want to customize your application for it. The compiler is a local reducer, so it does exactly the same thing as the reducer, but it is done locally in the same inside the mapper process. This is the goal here is to reduce network traffic. So embedded are partially reduced inside the mapper process, and so there is this helps reducing network traffic. The record reader is the component that has the responsibility of actually reading files and translating a stream of bytes into a stream of records to be fed to the mapper. If you don't specify record reader, the default is to simply feed lines of text. Pydoop assumes the input is plain text and feeds lines of text to the mapper. The partitioner is the component that decides which key has to go to which reducer. Again, if you don't do anything, you get the default behavior that is to use a hash function of the key in order to try to achieve a good load balancing and give roughly the same amount of keys to each reducer. And finally, the record writer is the component that actually writes output data to the distributed file system. And the default behavior here is to write key value pairs as kind of separated lines if you specify your own component. So let's see how to get a working Pydoop installation. It says Pydoop on your laptop. This might sound weird because I just said it's a framework for 1,000 of nodes and a cluster with 1,000 of nodes and things like that. But you can to play with Pydoop and try out some things. You can also bring it up on a single machine. Is what if you look into the Pydoop Quick Start guide, it's called pseudo distributed installation because everything you bring up all daemons as you would in a real cluster, but they're all on the same machine. So every role is played by the same machine. The first thing you have to do is to set up passphrase-less SSH. You have, since Pydoop communicates through SSH, you have to be able to log in without a sublime password. So you have to store the password, and this is how you do it with SSH key down. Then you have to perform at least a minimal amount of configuration. The only required thing is to specify where Java is installed in your machine. Pydoop has to know where to find Java to work. And then there are some other options. But not all of them are necessary, but the most important files are three XML files: HDFS site, MapReduce site, and core site.xml. Basically, you have at the minimum you have to specify where you want your data, HDFS data, to be stored in the local file system. In MapReduce site, you specify options for the MapReduce framework. You tell which local directory to use as a temporary directory. You can also specify the number of concurrent tasks. This is important because you do not want to underutilize your machine. So if you have, let's say, 2 or in this case, this notebook has a dual core, so accept this number 2 in order to use them concurrently. And you can also specify the options for the JVM, and there are, in total, there are around 100 configuration parameters, so you can try many different configurations, but most of them only apply to a large installation. Okay, after doing your configuration, you have to format the file system. That is, right, give me the data in the main node, so you're ready to use the file system and start the daemons. You can start all of them with this command start all stage. And a nice feature of it is that it comes with an embedded Jetty web server. So you get to the nice web interfaces for the distributed file system and the MapReduce framework. This is how the file system interface looks. You get several statistics on file system usage, status information, and you can also browse the file system and look at the files and directories. There is also a shell that works from command line, which is designed to be similar to the ordinary Unix shell. So it's kind of it's kind of easy to use because if you're already familiar with the ordinary EX shell, you get similar commands like ls, du, and the ordinary commands. But you can also use the web interface if you want. And this is how the MapReduce interface looks. You have, again, a lot of information. This is mainly used to monitor running jobs, failed jobs, and things like that. You have the total number of maps reduces, the total number of submitted jobs, the total MapReduce capacity. This is simply the number of concurrent tasks. Remember the option that you set before in MapReduce.xml, multiplied by the number of nodes. In this case, there's only one node, so the total is 2. If you had 10 nodes, it would be 20, for example. And you can use this interface to monitor jobs. And you can also, it's very sophisticated. You can go in deep detail and for each individual task, and it's also a useful tool for debugging. Okay, now that you brought, pardon?
Let's say your problem is you're running more than you want to. You can have
are you talking about killing the whole job or individual tasks?
Individual tasks.
That's not. You decided the total number of tasks before, so that's not the decision you typically take while the job is running. What is your concern? You think it might be harmful if there are too many tasks running?
If I got the parameters wrong the first time, and this is going to take a long time to run, I might want to change things on the fly if I notice that I didn't do it right the first time. Rather than restart.
No, you typically can't change things on the fly. You're better off keeping the whole thing and reconfigure and start all over again. It might be better. Mastering the configuration of loop it takes a while. It's not that easy. You might not get it right the first time. It's something you have to expect. Okay. Now that we broke up our Hadoop cluster, just to see if everything works correctly, we can run the Java word count example. We copy some input data to HDFS. We run the word count example, which is stored in a Java file, which comes with the Hadoop distribution. And after the Java is finished, we can copy our output back to the local file system. There is one output file for each reducer. And in this case, there was only one reducer, so I only have one output file. Its part are 5 zeros. That's an index every. So if I have two reducers, get apart 5 zeros and then 5 zeros at 1. Okay. You also, apart from output files, you also get a directory with a recap of the configuration in this XML file, and the job log, which is a detailed log that tells you what happened, statistics for each individual task, for each task attempt. So you can also post-process this log and get a lot of information on what went wrong and stragglers and everything. So it's a very detailed job. Log. Sorry. Okay. So at this point, you might want to write your own MapReduce application. But probably you don't want to write it in Java because the Java API is huge, and maybe you want just to start writing and without having to read a long API documentation. So what most people do at the beginning, is using the streaming library because it's the fastest path to write a MapReduce application. With streaming, you can use any executable as the mapper or the reducer. This works because in this case, these executables are seen as black box processes, and communication with the framework is done through standard input and standard output. You read key value pairs as tab-separated lines, and you also, after you finish computing your MapReduce function, you also write these values as tab-separated lines. So it's a simple text protocol. There is a lot of serialization going around, and this, of course, adds some overhead. But in this way, you can. The main advantage of streaming is that you can use any programming language because it's black box. It's only a process that communicates through standard input and standard output. So this is how you would do it in Python. This is this is only the number script. It's a bit different with the reducer. We will see it in a minute. So the mapper is quite simple actually. You just read the stream of lines from standard input and split these lines to get the words, and emit the word itself on the number one as a key value pair. But this is the reducer. Okay, it's not that big, but compared to the mapper, it's more complicated. Why? Because another big difference with the Java programming model and the official programming model is that you don't have a reduce function which is called a framework, where you get a key and an iterator over values. It is different. It's as the word streaming says, it's a stream of key value pairs. So all you know, it's guaranteed that you have a stream of key value pairs which are sorted and grouped by key. But you have to group them yourself, and you have to manually check whether the current key has changed. And this is very awkward. It's not difficult, but it's not natural either. You don't have a nice interface with iterators. You have to accumulate things manually, as you can see, and check whether the key has changed, and so it's kind of awkward. This is one of the main reasons why you would not want to use streaming. So, what are your options if you want to write a MapReduce application? Java is if you want to write your programs in Java, well, that's going to be maybe the best solutions if you really want to do it, because it's the native API. It is full featured. You can do anything the system allows to do, and it is the native API. There is also a C++ API, which is called Pydoop. It's included in the distribution. And there are also some options with Python for programming in Python, but not all of them are equal. There are some differences, and we will see them in a few minutes. Our motivation was what we wanted to achieve was we wanted to be able to use any extension, reuse existing code, be able to use to write specialized components, because sometimes you need to customize those phases and to access HDFS. And as we will see, not all of the Python solutions have these features. Okay, first of all, there are the two solutions which are integrated into streaming and Java. With streaming, we've already seen how to write a program with streaming. It's an awkward programming style. You can only write the MapReducer, yet there is no way to write the record readers, partitioners, and all additional components. There is no API to access HDFS, and up to, but this is not the case anymore in the trunk, and but up to initially you could only use a text protocol. You were not able to process binary records. And Jython is Jython. It's not CPython, so there are several reasons why you would not use Jython. Mainly the fact that you're limited in the number of packages you can use, and other problems that there are also several third-party solutions. We can roughly divide them into two main classes: Hadoop-based and other MapReduce implementation. Regarding the latter, we've already said that no matter how interesting they can be, they're not as big as Hadoop. Hadoop is the most widespread solution. You're not likely to encounter one of these frameworks installed on your cluster unless you own the whole cluster and you can do anything you please with it. The most important implementation is Hadoop, so you're better off trying to program on Hadoop, because the other implementations are not nearly as widespread and production ready. So, for what concerns Hadoop-based implementations, they are either based on streaming or Jython, so they basically suffer from the same problems. The most used one is Dumbo. Also, EuroPy is similar, and there are wrappers around streaming, which allow for a more natural programming style. They basically make it easier to run programs because you have a nice interface, but under the hood, they're still based on streaming. So apart from the ease of use, they basically have the same problems. This is a summary of what we wanted to do when we started out writing our own API for MapReduce programming on Hadoop. We wanted to be able to write all the additional components, or most of them, to get an actual programming model with iterators and all that stuff. And we wanted to be able to use any module, to use CPython, and we also wanted to be able to access HDFS. So what we try to do is to get the best of both worlds. As you can see, Streaming and Jython have different problems. Okay, what you can do with streaming you cannot do with Jython, and vice versa. So we try to get the best of both worlds. Actually, the API is not with Jython, since you can get access to the full API. You can do the same things you would with Java. With Pydoop, it's not actually complete, but you can write all the components I mentioned, and that's for most applications. That's what you really need. So it's more than enough for the most part of applications. So some words about the architecture. Pydoop is based upon Hadoop Pipes, the C++ API. Pipes is a framework where your application resides in a separate process which communicates with the main framework through a specialized protocol. Communication happens sockets with the framework. Your application provides a factory function, which is used by the framework to instantiate your classes, and then the framework calls methods, MapReduce methods on your classes, and get us the results. And our data flow is serialized and goes back and forth through this specialized channel. Pydoop is so since pipes seem to have all most of the features we were looking for, we implemented the Pydoop by writing Python extensions for the C++ and libHDFS modules. Pipes and libHDFS is a C API, which is also included in Hadoop and allows HDFS access from C. So, and it's differently from pipes, libHDFS is implemented as a Genie wrapper for the Java HDFS API. So, these modules are then supported by some pure Python modules which make up the Python API, and then there's the user application that uses the Pydoop API to write the programs. So this is a usage example. Again, the word count program. This is the entire word count program. If you remember the Java one, where I removed the leading imports and the turning main. In this case, this is the whole program. So it is much more readable. Of course, it's much easier to write programs in this way. It's much less verbose than the Java one. So this is the complete program. This is an example of how you can use the API to do additional stuff like status reports and using counters. Status reports are simply text messages you send to the framework to communicate the status of your application. In this case, I'm simply telling the framework when I'm initializing the number. And counters are some variables you define that keep track of anything that's relevant for your specific application. In this case, I'm counting the number of input words I've seen while the processing continued. And this is where status messages and counters end up. In the MapReduce interface, there is a task table, and there is a column for the stages, which is updated in real time. So this is where my initializing message ends up. And there is also a counters table. As you can see, the counters defined by my application are not the only ones. There are also several other counters which are automatically added by the framework. Okay, this is an example of how to write one of the additional components. In this case, this is a plugin replacement implementation of the default Java record reader, which feeds text lines to the macro. And this is also a first example of how to use the HDFS module. So the record reader is a component that actually deals directly with the HDFS files. In this case, we are before the mapper. We have to read the file and extract the records and feed them to the mapper. So the input from the context object, I forgot to say this, also in the previous examples, the context is an object passed by the framework, which is used for all communication between the framework and your application. From the context, you get key value pairs, you emit output key value pairs, you emit status records, you get counters. It's a single point of interaction between the framework and your application. So, in the case of the record reader, from the context, you can also get the input split, which is a logical description of a subset of the input data. Specifically, in this case, it's described through an offset, a length, and a file name. So I get the file name from the input split. I can open the file with the HDFS module and seek to the offset and read up to the end of the split. In this case, I'm using a readline method that it's a method that we added to HDFS files because it was not present in the original with HDFS. This is mainly because we want the HDFS file to be as similar as possible to ordinary Python file objects. We have to implement two methods in the record reader. Next method, which is the one that actually emits records for the mapper. The output value is a tuple of 3 elements. The first one is a boolean, which says if we have a record or not, and the other two are the key and the value. So, first of all, we check if we are at the end of the input split. In this case, we return false because we don't have any more records. Otherwise, we build a key value pair and emit it to the mapper. In this case, I'm reproducing the default behavior, which is to emit the byte offset into the file as the key. And the value, this is typically not used, and the value is basically a line of text. There is also a getProgress method that we have to implement, and it simply says, tells the framework how far we've gone through our data. So the amount of the ratio of input data that we have already processed up to that moment. These are also re-implementation of the default record writer and partitioner. In the record writer implementation, there is also an example of how to read configuration parameters. In this case, I'm reading standard Hadoop configuration parameters, but you can define your own. You basically can define any number of properties for your application which allow to customize it. The user writes an XML configuration file which is very similar to the ones we see for the general cluster configuration, and so you can define any property, please. In this case, I'm reading standard ones. I'm retrieving the current partition, the name of the output directory, and the output format separator. So what do I have to put between the key and the value to serialize them before writing them to the file system? In this way, I can build the file name. I know where to write it, which directory it has to go into, and I can write the tab separated. In this case, the default is a tab, but it could be something different if you specify a different separator, and so I can serialize the output and write it to the output file. So we also have an example of a partitioner again. This is a re-implementation of the default one. The partitioner only has a partition method, which receives the current key and the total number of reducers. What you have to do is to decide which reducer. You have to return the number, the index of the reducer where you want to send that key. And this is a implementation of the default behavior that simply uses a hash value of the key for doing that. Okay, this is an example of usage for the HDFS module. As I said, we tried to make it as similar as possible to ordinary Python 5 objects. There is also some additional information. File holds a reference to its file system, which in turn also reference to the hostname and port. But for the most part, you get the same methods you would expect from ordinary Python 5 objects. So read, line, open, close, and the usual things. A difference here is that if you do f.name, you don't get the relative path as you would with the ordinary file objects, but you get the whole qualified, fully qualified HDFS address for the file. This is an example of how you would use the HDFS module to compute some statistics on HDFS usage by block size. The block size is a property of each file, which is simply the size of data blocks. By default, the block size is 64 megabytes. It's much more than ordinary file system for performance reasons. But you can specify different block size for each file you store into HDFS. So let's say you have a lot of files with different block sizes in your file system, and you want to get statistics of HDFS usage by block size. This is an example of something you cannot do with the built-in HDFS shell that ships with Pydoop, but you can do it in utilized code with the HDFS Pydoop module. It's very simple. There is a function that recursively walks directly tree starting from the root, and then there is a function that uses a counter for keeping track of usage for each block size, and then a shortening program that walks the directory with these statistics and then writes the output writes the final output. Okay, some words about performance. This is a test we ran on a cluster at our site. We wanted to compare Pydoop with the other solutions for MapReduce programming in Python. And the Java C++ figures are here just for reference, because of course we're not comparing, but the thing is, we wanted to just compare with other Python solutions, because once you have decided you want to program in Python, you're interested in how the framework compares to other Python solutions. And between the error range, it's about the same. Python has about the same performance as Python, but streaming turned out to be much worse. This, of course, it's an IO-bound application, where count from the computational point of view is very, very lightweight. So, but we decided to use an IO-bound application, because if it were heavily compute-bound, probably it would be unfair, because C++, we expected C++ to win easily. So we wanted to see how the different solutions interact with the framework, what kind of overhead they have. And of course, Java is the fastest, because there is no overhead. It's the basic framework. Pipes is based on Java, so it adds some overhead, and Pydoop is in turn based on pipes, and so of course it has some more overhead. But that's true of any problem where you choose to use Python instead of C++. So you're not worried about much about performance, but if you're interested in the speed of development, the ease of use, so it's basically the same as it's every time you choose Python instead of C or C++, it's the same thing. So it's not different when you're using a distributed computing platform. We also compare Pydoop to Django. There is a difference here because Django's authors submitted a patch for streaming, which allows to use binary records, and this makes things better. As you can see, there is it's much better than plain streaming with plain text records. But we found out that it's still slower than Pydoop in this case, probably because there is still more serialization or overhead than in the Java and pipes case. Even though with binary serialization things get better, it's still slower, but not as much as with plain text streaming. Okay, finally here is a summary of what we use Pydoop for at CRS4. It's not a project, we actually use it in production. We have a sequencing and genotyping platform that produces a huge amount of data. We do have our personal data deluge in our company because we have 6 Illumina sequencers that produce about 4 terabytes per week of data. And we wrote an application, Pydoop.sourceforge.net is published, it's out on SourceForge. And this is for short read alignment. Basically, the way sequencers work is to fragment DNA into a large number of short fragments that then have to be aligned to a reference genome. And this is a very computationally intensive task. So we wrote a parallel application with Pydoop for this, and we're currently using it in production. We've also parallelized a genotype cloning workflow. But the guys that were running the workflow were taking about 2 weeks to perform genotype coding on 7,000 individuals. With re-implemented this application for Hadoop with Pydoop allowed us to reduce running time to less than 1 day. So it's a big difference because you can also think about doing executing the run 3 or 5 times and check for errors, tweak the configuration parameters to see what changes. If it takes 2 weeks to run the whole thing, you cannot even imagine doing such things. And it's also more resilient because Hadoop has a high fault tolerance, so you don't have to fear of losing a node and if you don't have a resilient structure, if a node goes down, you've lost everything. So you don't have to be afraid of such things when you're using Hadoop. There are also other applications under development, RNA sequencing, flow cytometry. This is a work in progress. So to summarize, MapReduce is a big deal. It's a great framework which allows to, it's especially good if you have to process huge data sets and which is highly scalable and relatively easy to use. There is production level open source implementation, Apache Loop, and we contributed an API for programming, for writing programs in Python with Pydoop, which is called Pydoop, and it's available at pydoop.sourceforge.net. Finally, some acknowledgements. Part of the MapReduce tutorial is based on the Sigmetrics 2009 Google tutorial on MapReduce. The free lunch is over, as I said before, is one article by Art Sutter, which is available online. If you haven't read it yet, I suggest to read it because it's quite interesting. And finally, Python's rules. That's what I used to highlight the code. It's a great package. Check it out. And that was all. Thank you for listening.